In this video, we're going to explore my Infrared Rememberizer project. I have a lot of students who are interested in making media artworks, which is basically a monitor and some kind of player that loops some kind of media content. Now, a lot of these students don't have money, and the cheapest and easiest way to do it is to buy an off-the-shelf LCD TV. They're dirt cheap now, and most of them have built-in media player functionality. But the problem with that whole scenario is that as soon as you pull the plug and turn it back on again, it's dead. The TV defaults to off. And if you have other multiple devices, getting it all back and working is an exercise in infrared hoop jumping, where you have to go through menus and turn things on and off in the right sequence. And it's really a pain. Because I always tell my students, if you're going to make any kind of electronic, interactive, media, whatever kind of artwork, and you're going to put it someplace, you better make sure that it completely recovers from a power cycle. You got to be able to pull the plug out and plug it back in, and it's got to come up and it's got to work. Otherwise, your artwork is a failure. It's not going to work. Someone's going to turn it off, something's going to happen, and it will not be turned back on by anyone because nobody else cares besides you. And that's just the reality. So if you want to win, you've got to make it auto-recover 100%. So that's just a little bit of philosophical advice for anyone contemplating electronic and media artworks. So what this device does is it just allows you to start a recording session, fiddle around with all the remotes exactly as you would when you're starting it up for real. In fact, you'll want to watch your boxes to make sure they do what you want. It just records it all, and then when the box gets powered up again, it just emits those infrared signals exactly as they were when it received them. And that allows you to automate the whole process pretty much effortlessly. You just make this little infrared thing power up at the same time as your other crap, and it all comes on and works. Problem solved. I prepared the TV monitor with a USB fob containing the media that I want to play. This particular monitor is going to be buried inside of something, so I can't really even point the remote at it. So I embed a piece of fiber optic cable that's glued in so it points right at the receiver. That way I can use my Rememberizer and even a remote by just shining it into the end of the cable, and it controls the TV pretty well that way. I programmed the Rememberizer with all the sequences of commands that are required to turn the TV on, find all the right menus, and get the media playing in loop mode. And we're off and running. We begin the recording session by powering the board on with the button pressed. The red light indicates record. The green light shows us the infrared commands being received and stored. When we're done recording, we stop the record by pressing the button again. The next time you power the unit on, it will just automatically play back the sequence with exactly the same timing that you recorded it. As simple as it could possibly be. So let's take a closer look at this whole idea of infrared communications. It all begins with light, specifically light at around 950 nanometers, which is well below the visible range. Now, there's a lot of other sources of light at this wavelength, like incandescent light bulbs and even the sun. So to make this really work and to be able to reject this interference, we rely on a system that is very similar to radio. We actually use a carrier wave. We modulate this light by pulsing it at a specific frequency that narrows the bandwidth of the whole thing so that our receiver can just look for pulses of light that are around this frequency and only respond to those. Now, if we look at the data sheet, we'll see that they come in different carrier frequencies, and these range literally from about 20 kilohertz all the way up to about 60 kilohertz, depending on who makes them. If we look at the block diagram for the typical infrared receiver module, we can see there's actually quite a bit going on in there. Its job is to receive these light signals which can vary over a huge range of intensity. Like if you're standing all the way across the room, or you walk right up to the appliance and stuff the remote right at it. That could probably be a range of like 100,000 to 1 in brightness. So the first stage after the input is the AGC, or automatic gain control. Its job is to adjust the gain depending on the signal level and try to normalize it so that it's all around the same level so that it can be detected. The next stage is the bandpass filter. Its job is to reject all light pulses that are not modulated at exactly the correct center frequency of the filter. This is how we can achieve a large signal-to-noise ratio. The next stage is the demodulator. Its job is to remove the carrier frequency and provide us with only the digital signals that we need to decode the command. This feeds into an open collector transistor that provides a digital signal out to the microcontroller. If we look at these infrared signals captured on an oscilloscope, we can see they're made out of bursts of pulses centered on the carrier frequency, in this case 38 kilohertz. These pulses vary in width and spacing. This is how the digital information gets encoded. The typical infrared command packet begins with a long burst. This burst is there to help the AGC system stabilize on the incoming signal level, so that when the tricky data part comes along, it's already locked on to the correct amplitude so it can decode it correctly. Let's explore the behavior of one of these little infrared modules a little more carefully. They're so highly optimized for their task that they're kind of useless for anything else. I was always tempted to try to make some kind of break beam detector thing out of it, but I quickly realized that would really be a total fail because they don't like that kind of operation. For example, if you just send them a continuous carrier with no bursts or modulation, it craps out completely like it's not even there. Totally strange. They're also very sensitive to the number of pulses within a burst, with a certain minimum that just doesn't get seen at all. And of course, the carrier frequency needs to be pretty accurate, because outside the pass band they become less and less sensitive and more jittery. In practical terms, our device should take this complex digital waveform coming from the remote, store it in a flash memory, and then be able to play it back with enough fidelity so that the receiving device does not know the difference. The most efficient way to store this data would be just to decode it first and then just store a couple of bytes. But that would imply that we'd have to understand how to decode pretty much every remote code there is on the planet, and that's pretty tricky and not very practical. So we need to figure out a sort of code agnostic way to store this information, so we don't care what the protocol is, we just store it as a waveform. The simplest brute force solution would be just to sample the waveform as a single bit on or off and compact that into bytes and then stuff it right into the flash memory. But this approach is terribly inefficient. If we look at the maximum carrier frequency of 60 kilohertz and realize that the Nyquist theorem requires us to sample at double that frequency, we'd end up having to sample at 120 kilohertz. At that frequency, a 1 megabit flash memory, which actually contains 131,000 bytes, would only be able to store 8.7 seconds worth of recording. Terribly inefficient. If we study these infrared waveforms carefully, it can be seen that they have a lot of things in common. Even if their protocols vary dramatically, they're always made up out of bursts of a fixed carrier frequency in whole numbers of cycles separated by pauses of varying lengths. If we know what the carrier frequency is, we can encode these complex signals simply by noting the number of cycles in a burst and the time between bursts. With this scheme, we can make a dramatic improvement in the storage efficiency of our whole system. At the beginning of each new infrared command packet, we carefully measure the carrier frequency and store this value. This is then used to reproduce the carrier frequency exactly. After a period of inactivity, the system will rearm so that the next command packet coming in will get resampled and stored. This way you can have multiple different remotes within one session, and each one will have its carrier frequency reproduced exactly. So how do we store this information in our flash memory in an efficient and clever way? Well, let's define a 16-bit data word, which is 2 bytes, and basically use the top 2 bits to specify the meaning of the 14-bit payload. The 2 bits gives us the ability to define 4 different things. In this case, 00 defines the number of delay cycles, 01 defines the number of burst cycles of the carrier, 10 defines the period of the carrier, and 11 is an end of record marker that ends the playback. The key to this device is the precise ability to measure and reproduce timing delays. Almost all microcontrollers these days have multiple counter timer resources with little peripheral engines that allow you to capture and measure timing events with astonishing precision. This particular device uses 2 counter timers, one that runs at 125 kilohertz and another that runs at 16 megahertz. The slower one, 125 kilohertz, has a timing resolution of 8 microseconds. We use this one for the overall timing of delays between packets. The 16 megahertz counter has a timing resolution of 62.5 nanoseconds, which gives us great timing resolution to measure the period of the carrier frequency. By using these timers and counters, we can both measure and reproduce these signals very accurately. I'm not going to go into agonizing, painful details as to how the code actually works, but suffice to say that this is fairly straightforward stuff to do with just about any microcontroller. The first version of the hardware was super simple. I just used a resistor and a phototransistor to receive the raw infrared signals from the remote. The flash memory was a 3.3 volt device, but my CPU is 5 volts, so I made a crude level shifter out of some resistors. Super basic, but totally worked. For version 2, I started getting delusions of grandeur and feature creep started to rear its ugly head. First, I added a preamp for the infrared input signal, so you could hold the remote farther away and it would still receive the signals. I also added a more powerful IR LED driver so you could get a bigger range on the output. Then I started to think about how you could make this thing a shield for like an Arduino or a Raspberry Pi and use serial commands to just trigger the transmission of these infrared commands. So I added a header and a whole bunch of extra parts, and I haven't really implemented that whole idea, but it's still kind of buzzing around in the back of my head. I also found this interesting part that Vishay makes. It's an infrared sensor module designed exactly for learning remotes. It doesn't care about the carrier frequency. It actually outputs the raw signal just like my preamp does. I thought about using this, but I'm a little scared because it's one of those esoteric sole source parts that when you go to produce this thing, they know heavy, and then you're totally up shit's creek. So I think I'll just stick with my little roll your own preamp circuit. It's a lot safer that way. So that kind of wraps it up for this project. Tell me what you think I should do with this thing next. Should I try to make this into some kind of product, like some way to sort of simplify integrating infrared control into your projects, or just leave it as it is? Tell me what you think in the comments. As always, I hope you learned something and enjoyed watching this video. Thank you very, very much.